Right. So very good day to everybody present here. So today's class about information technology in bioinformatics and genetics. We discuss about ML algorithms, machine learning algorithms. I hope you understand the meaning of ML, machine learning. It is about prediction analysis and algorithm. Okay. Like what will be this model after 2 years? What will be the model after 5 years? How the process will take into. So that's ML. And here in this today's class, we discuss about DP, dynamic programming, and then we discuss about gradient descent, about the EM as well as GEM algorithms, and then we discuss about the Markov-Chain Monte-Carlo method. You call it as MCMC, Markov-Chain Monte-Carlo methods. Yes. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, let me thank God for giving me this golden opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. So today's session we will discuss about DP, dynamic programming, and then we discuss about the gradient descent. We discuss about random direction descent, that is one type of descent. Then we discuss about EM, expected maximization, and Gaussian expected maximization algorithms. We discuss about the E step as well as M step, expected step as well as maximization steps. Then we discuss about BG distribution, Boltzmann-Gibbs distribution, and then we discuss about some sequence of estimates. Then we discuss about MCMC method, Markov-Chain Monte-Carlo method, and then we discuss about the efficiency. We discuss about the Markov chains, and finally we end this class with the ergodic distributions. So I've given the innumerable works, please go through them, please complete them at your best available time. And at regular intervals, I will be giving you some short videos to discuss the knowledge in our topics. So this is dynamic programming. It is actually an optimization technique. You can apply it on any problem. You can generally apply it recursively. So the main problem you are going to subdivide. So this is dynamic programming. You can call it as a general optimization technique. So what you do generally, a bigger problem is divided into smaller problems. Okay, so this smaller problems of small size, you are going to apply a solution for each of the problem of small size. You are going to apply a solution. So finally you aggregate this solution and finally you make it up as a the larger solution to the larger problem. Okay, so as you can see, the main problem is divided into sub problems, and similarly the main solution is divided into sub solution. So for this, we apply a prototype problem to the in which you are going to apply this dynamic programming. So between two nodes, you are going to find the shortest path. For example, let us take the case from this node. Okay, we have 3 nodes, and then there is destination. Then you find the shortest distance. Okay, for example, to reach this particular place, okay, either you can go straight or maybe you take a side road and then you can go this one. Okay, so what is the shortest path? What is the shortest cost to reach the destination? So that is what you have with the dynamic program. Let us consider an example. We have the shortest path from node A to node B through the node C. Okay, so maybe you can take the shortest path from maybe A to C with considering the shortest path from C to B. Okay, so that also you can take. That's what I told you. For example, if you want to reach the Sindbad Cafe, let us take the case from this particular place. Okay, so maybe you can go straight, or maybe you can take a short path and then reach there. That is your problem. But which is the shortest means? For example, this path takes maybe 7 minutes, and the shortest path takes 5 minutes. So you take the shortest path. Normally you don't prefer the longest path, you take the shortest path. So this is actually based on the Bellman principle. Okay, so a general solution for this original problem is constructed by recursively piecing together the shorter optimal paths. So this is dynamic programming and its variations. Here you have now the model and previous experience. You have to plan on the value and the policy, and there is a direct route to the value or policy and how you try to react. Okay. So here you will apply some Viterbi coding decoding algorithm. Generally, it can be applied to the electrical engineering. The same thing you can apply in the bioinformatics also. So here we find the shortest path in the appropriate graph with some definite parameters. Okay, so you are going to find the shortest path using the dynamic programming, and generally you are going to align two sequences generally of length n. So you are going to find the shortest path with some maybe n2 indices, I mean vertices or indices. So dynamic programming, using dynamic programming, you can find the shortest path, you can find the order of that particular vertices. So it is given as order of n2. So whenever you are talking about dynamic programming, it is not without the RL algorithm. RL denotes the reinforcement learning. So reinforcement learning is something like you try to learn, you try to adapt a particular network, and you try to train that particular network. You try to model. Okay, for example, you are working in a particular company, and that particular company requires C++. Okay, then you are working on that particular project, and afterwards comes COVID. Now what you have to do? You have to sit in your homes. You have to still upgrade your skills. So which means your model has to be trained, has to be upskilled. For example, if you are in 2022 and remember you are in 2025, you cannot say I have the same skills. No, every month you are upgrading some skills. So the same way, the model has to be trained, has to be reinforced every now and you have to compute the likelihoods as well as you have going to align the sequences with regards to hidden Markov model. Okay, so with the training as well as exploitation phases, we try to aggregate the likelihoods and you try to align the sequences. So this is the basis. RL is the basis for dynamic programming. And this is gradient descent. So whenever you have to calculate the parameter estimation, you have to find the best possible model. So it is given as m of w. Okay, that is the model. Okay, which is going to minimize the posterior function f of w. So generally it is given as the negative of the logarithm of the probability function. So it is minus log p of w by d. The likelihood is exactly the inverse of the algorithm. So it is minus log p of d by w. But posterior f of w is minus log p of w by d. Likelihood is inverse, minus log p of d by w. So from this we calculate the gradient descent. So it is given by w of t plus 1 is equal to w of t, the present function, minus eta. N, you shouldn't say n, it is eta. Eta is nothing but the efficiency factor. So eta into dou f by dou w power t. So this dou f is nothing but the posterior function f of w divided by dou of w. W is nothing but the sequences. So this eta is nothing but the step size, okay, or maybe the rate of learning, okay, rate of learning that particular model. It can be kept fixed or it can be made variable, it can be adjusted according to the learning process. So from this you calculate the gradient descent based on the different implementations of the training or maybe learning model. So whenever you are talking about ML, machine learning, definitely it should have neural network. So it will have like maybe back propagation network, like feedback network, feed forward network it will be having. So with regards to this ML, we would be having back propagation algorithm. So this one it will be having in addition to the hidden Markov model, where we would have the forward as well as backward procedure. Okay, so backward propagation network means the output would be following the input, but in the case of forward it will be from input to the output. From here then it branch out, from the branch out it goes like this. This is feed forward. Feedback network is back, reverse part. Okay, for example, That's what I told you. From here you reach Sindberg Cafe. This is forward network, and from Sindberg Cafe to reach this place, it is backward network. Like it is going like maybe from this place, maybe 10 of them are going to different places, and all the 10 of them join together at one common point. So this is feedback network. So it is generally very essential to run the procedure several times so that you can know about the different starting points and you can learn about the learning rates as well. So for this, this plain gradient descent that we talked in the previous slide is actually very slow. Okay, or it can be considered inefficient for some situations. Okay, so that is the reason in order to overcome the problem, we will have a conjugate gradient descent. Okay, so that is the way you will have the second order information and you will have more of the complex situations in it. So definitely you can have a previous experience of the training model. It will be helpful for updating the required model. So this is a random direction descent. So that's an updation of the descent algorithm. So here we would have calculate the local minima of the function. Okay. So for this we would calculate the random perturbation of the current estimate. So if it is lying below the current level, then we would be calculating this current estimate. So all these current estimates will be helpful for reinforcement learning, for updating the required training model. So in order to determine the direction of the descent, we go for the random direction descent. So each of them would be generating a new direction, and generally with regards to maybe line search or maybe random descent, so that you can find it in the expected maximization algorithm. So these are the three consecutive points of expected maximization algorithm. So we will have the likelihood surface f of w. So that is nothing but the posterior function. If you remember from this previous slide, f of w is equal to minus log p of w by d. Okay, so this one we are going to take this one. So from this, the likelihood is actually inverse. So f of w is equal to minus log p of d by w. Okay, so this expected maximization algorithm is going to minimize the surface g of w with g of wt equal to f of wt. So that would be given to the surface area A. Okay, so here w equal to wt for when the surfaces have the same gradient. So w equal to wt when the surfaces have the same gradient. So for this we will have like a, B and C. So A point you are calculating from WT and B and C from WT plus 1. So this one C point is determined from the slide by calculating the new posterior on the hidden variables from D to C. Okay, so this is W power T and W power T plus 1. Okay, so from this curve. So this is the generalized expected maximization algorithm and expected maximization algorithm. So in the previous slide you saw about 3 points A, B and C. From A and B you calculated C. Okay. So from this you are going to calculate the generalized expected maximization algorithm. So here the expected algorithm you will be having the hidden Markov model. Okay, so that is HMM. Okay, so from this you are going to have the concept of free energy. We are going to generalize this particular model. So that is the way you call it as generalized expected maximization algorithm. So if you see in the this image, it's a GIF. Okay, it's a GIF image. So we will calculating the delay as well as duration. Here, if you can see in the diagram, the likelihood is changing. See, it is changing. From here, it will be changing. The original point is that yellow point, and from there, it is going to change. Okay. So this expected maximization algorithm generally for models, for training the models, and similarly with the situations of several hidden variables also you can use this particular expected maximization algorithm in order to find the hidden as well as observed variables like p of d comma h by w. we will have, you can have the hidden variables as well as situations with generalized structures. You can use this EM algorithm, and if you can computationally follow this expected maximization algorithm, it's actually difficult to find out this P of D by W directly. So what you have to do, you have to optimize it. So that is the way we go for generalized expected maximization model. So that is the way you are going to optimize this expectation E of log P of D by W. So we are going to optimize it. So E of log P of D by W is equal to E of log P of D comma H by W minus log P of H by dW. So this step is nothing but you are going to go with the optimization. Okay, so that is the way you are going to optimize the expected step as well as maximization step. So if you can see in the diagram, so it will be E step, we will be having updated variables, so that should be the final output. And then in the maximization step in there, you will have to update the hypothesis. Hypothesis, it is nothing but the imaginary conditions. Okay, so that thing you have to update, and you have to make sure that it gets interchanged successfully. So during the E step, the distribution of hidden variables is being computed given the observed data and the current estimate of W. And during the M step, the parameters are updated, which means the hypothesis is being updated given the presumed distribution on the hidden variables. So we go into the BG distribution, Boltzmann-Gibbs distribution. So here we want to extend the E step as well as M step. So earlier we discussed about expected step as well as maximization step. So here you are going to compute this distribution Q multiplied by H over this particular H histogram function. So here we will have Q multiplied by H, which is equal to probability of H by D, comma WT minus 1. So this is actually the previous weighted function. Okay, and then in the maximization step, we will be setting this WT equal to argument W max of EQ multiplied by log P D comma H by W. So if you can see in the diagram, we can see the Boltzmann-Gibbs distribution of some function. Okay, so we'll have like 20,000 updates and 10,000 updates. You will see a spike for more number of updates than for the lesser number of updates. That's equally distributed in the 10,000 updates. So here we are going to define this energy, the posterior function f of h is equal to minus log p d comma h by w. So this Boltzmann distribution function is given by the posterior function, which is p of h by d comma w. So this will be having at the factor lambda equal to 1. So both the f of the posterior function f comma q comma 1, which would be equal to the posterior function w comma q comma 1, which is equal to both of the function f comma q and w comma q, that will be equal to, so f of w comma q, which is equal to expected function e of q of f minus h of q. So this is the step with categorizing the parameter at lambda equal to 1. So you'll be having two steps. One is E step as well as M step, expected step as well as maximization step. So you are going to compute the Boltzmann-Gibbs distribution Q multiplied by H, which is going to minimize the previous factor, which is W t minus 1. And the maximization step, similarly, is going to minimize the posterior function f of W t minus 1 comma Q star. So here you are going to calculate the free energy. So as I told you, GEM is all about calculating the free energy. So f of w comma q star comma 1 equal to minus log p of d by w. So these are nothing but like a mathematical function that you are going to calculate the weighting factor. Okay. So whenever you have to calculate the sequence of the estimates, you are going to go with the weighted factor wt comma qt, which is equal to wt comma that qt that you are going to go to the next step also. So qt plus 1. Similarly, the weighted factor also you can increment wt plus 1, qt plus 1, and similarly wt plus 1, qt plus 2, which means that keeping this one and incrementing this one. And next step, keep this one remains the same, you increment this one. So this is how it goes. Right increment, keep the left increment, keep the right. So that's how it goes. So WT QT, WT QT plus 1, WT plus 1, QT plus 1, WT plus 1, QT plus 2. So it goes for every time interval. So this also we will have the Wt comma q t plus t to be greater than equal to Wt comma q t plus 1. So everything it will be greater or it may be equal. So that is the condition for the sequence of estimates. And we will have f of Wt comma q t plus 1 is equal to minus log p of d by Wt. So this is how it goes with the expected maximization algorithm. It is going to converge to the local minima function f of w comma q. So this is how you are going to calculate this derivative of the function. So as I told you in the previous slides with the Wt plus 1, it can be given as the argument W function, minimum of minus log P d by W plus h of Qt plus 1 plus comma P h by W h by d comma W. So this derivatives, if you take the derivatives, then it will have if you take the derivative of g, so it gives dou g by dou w, which is equal to minus dou of log p of d by w by dou w minus summation over h qt plus 1 h dou of p h d by w d comma w divided by dou w divided by p of h by h bar d comma w. So you are going to categorize this function derivative you are going to take. So this is the function for when the weighted factor is equal to Wt, which is nothing but W equal to Wt, it becomes minus dou log P of d by W by W. Okay, so this is the function for which W equal to Wt. Okay, so this generally it will be an exponentially curve, so it will be rising exponentially. So this is the reason you call this posterior function, this g, to be always convex. So this is how it goes with the generalized expected maximization algorithm. So this is MCMC method. So it is nothing but Markov-Chain Monte-Carlo method. So here we would be using stochastic method, which is related to statistical physics, as well as we will be using this Bayesian model. You remember in the previous class we discussed about Bayesian networks, Bayesian model. So same thing, this Bayesian inference that you will be incorporating in MCMC method. Okay. So here we will be considering a probability distribution P of x1, x2 up to xn. So this expected function E of f is given by summation x1 to xn. We will have the function, the posterior function f of x1 up to xn, and then multiplied by the probability x1 up to xn. So it is given by 1 by t. As you can remember, the function can be given as the reciprocal of the time interval 1 by t summation t equal to 0 to t f of x1 power t up to xn power t. So this is how it goes with the application of the Bayesian inference into the stochastic model. So this is the Markov chain. So whenever you are talking about Markov chain, you should have to explore about the Gaussian mixture model. Okay, so here you will have this x1 up to xn is nothing but the distribution. Here you are going to employ this Markov chain where we will have the mean of the estimator, or maybe the expected, the average of the estimator to be E of f, and variance can be given as variance of f divided by t. So here in the MCMC method, you can still enjoy much more benefits with regards to high dimensional state spaces. Also, with the higher dimensional spaces, this MCMC method is considered to be efficient because you are going to generally rely on a single estimator, and you can incorporate this Bayesian inference models into it. Also, the another advantage is that you can calculate the value of P of E of f divided by t efficiently for any sample of t. So this is one particular example where we are going to use the Markov chain. For example, maybe there is nice climate now. Also there is some rain also. There is also snow. So there is some probability that rain can occur at this particular time. There is some probability that nice climate can occur. Also there is a probability that snow can occur. Okay. So maybe from rain to nice, the probability is 0.5. Okay, rain to nice. Maybe today it is hot. Maybe in the night it will be raining. So half of probability. Morning nice, night rain. Okay. Also from nice to rain there is 1 by 4 probability, 0.25. And similarly from rain to snow it will be having 1 by 4 probability. Similarly from snow to rain 1 by 4 probability. But from nice to snow, for example, if we are experiencing very cold climate, so there is half probability. From maybe from snow to nice, half probability is there. But from nice climate to snow, maybe like 1 by 4 probability. So each of them has its own probability. So we consider a system S will be equal to S1, S2 up to S of S. Will be having like S states. So we will have the probability P of S of t plus 1 bar S of 0 up to S of t equal to P of S of t plus 1 bar S of t. So this is how you catalyze the Markov chain, where we would have like different climates and we will have the corresponding probabilities. So this is a diagram where you can better analyze from A state to B state. From A it can go, for example in the previous diagram if you can see, rain it goes 0.5 probability. Okay, maybe from lower rain or higher rain there is probability of 0.5. Similarly for snow, so low snow as well as high snow it can have a probability of 0.5. So similarly for this one, from A to B, A to B it can have, B to A it can have, within A it can have, within B it can have. So this is the probabilities for P of S t plus 1 bar S of t. So we will have the transition matrix T equal to Tij. So the state space of the chain is given by the coordinates x1 up to xn. So they will be having, for each of the state we will be having the n dimensional variable. So this is the Markov distribution. We will have Q of Si equal to Tik Q of Sk equal to 1 minus summation Tji Q of Si plus Tij Q of Sj. So the sufficient condition is nothing but Tij of Qsj equal to Tji of Qsi. So if you interchange the variables, it should have the balanced equation for stability. And finally, we end this class with the ergodic distribution. So here, if you can calculate, in the previous case, you have Si, and it is transformed to Sj. So for the average number of transitions from Si to Sj, or maybe from Sj to Si, we will have to preserve the overall distribution for the states. So that is the reason you go with the ergodic distribution. So here, if you consider a Markov chain, it can have several stable distributions. But in order to calculate for the finite space, or maybe for at least one stable distribution, you should preserve the states. So that is the reason you go with the ergodic distribution. So you will have stable distributions. Also, you will have the stable finite spaces. Okay. So a distribution, this is a very important definition. A distribution is defined to be ergodic if and only if the chain always converges to it, irrespective of the initial distribution at time t equal to 0. So this is the way where we will be having one stable distribution. You call it to be the equilibrium distribution. Right. So these are the independent works. Please complete them. I can even show you right now how many independent works you have actually completed. So complete them. Algorithm design and problem solving, computational thinking skills and algorithms. So this is with regards to neural networks you should complete.